Vale, endavant.
Vale, espera un moment.
Ja estic gravant jo.
Estàs gravant tu, David?
Sí, sí.
Vale, perfecte. Hello, everybody. Today we have Jorge Comas. He's professor of statistics at Universitat de Lleida, no? If that is another Catalan university. As you know, he is from here, but he speaks English. So any question you can address the question in English or in Spanish. So we have a trilingual professor in Catalan.
And barely Portuguese too. So
and Portuguese. We have a couple of students that are from Brazil. So Jordi, Jorge, feel free to start. Thank you very much.
Thank you, David. All right, everyone. So my name is Jorge, but you're welcome to call me Jordi if it's easier to pronounce that for you. The idea of today, it's starting with generalized linear models, which is not a simple set of ideas. You are going to start with a brief introduction to common terms that we may use during these sessions. And after that, we are going to see the most basic idea of generalized linear models, which are correlation and linear regression. Okay, so generalized linear models, it's somewhat new idea in statistics, new as in from the 1970s. But linear regression is way older than that. But, well, it's within the scope of generalized linear models. Now, because I know that this group of people is not particularly trained in statistics or math in general, this is why we are going to do this brief introduction, well, brief, as long as necessary, to common terms that will come up. All right. So please, at any point, you are welcome to interrupt me. Just raise your hand or just speak out loud. I will shut up for you. So ask any question that you feel like asking. So first, I hope you can see my window here. I sent through David a Word document with a number of links to some statistics resources online that you could find easily, and they were also open source type material. So we are going to start there. In that document, we start from the openly licensed book, Introductory Statistics at OpenStax. And this is the first screen that you're seeing that I'm sharing. I'm sure that for some of you, this will be unnecessary mentioning some of these ideas, but just so we have a common fundamental understanding of the basics. All right. So first, most common term, average. It's also called mean. It's as it says here, it's a number that describes the central tendency of data. Okay, so not always useful. Average is just a number. It's just a number that describes a set of data. Okay, if this set has follows a particular distribution, average can be useful to describe that set of data. All right. So the most common, easily available idea to understand in terms of distributions, it's probably the normal distribution. All right. So the normal distribution, it's the distribution that follow a bell shape type of data. Okay. What do I mean with bell shape? Where central points are more likely to occur and extreme values are less likely to occur, and they are symmetrical. All right. So if you have something like that, for instance, if you can think of a test in an exam at university, if this exam was perfectly crafted and idealized, you may think that the average score would be 50%, and the extreme scores would be 0 and 100. And the closer you get to that 50%, the more people are bunched up around that number. And the closer that you get to 0% and to 100%, the fewer people are there. So in that case, the average or the mean would be a very good descriptor of that data. The other descriptor of normal distributions are standard deviation. Okay, so to describe a normal distribution, we need an average, a mean, that is the central tendency of the data, and we need a standard deviation. And the standard deviation basically gives us a description of how far away from the central point, from the mean, are the data points that we have. All right. If you imagine something with very little variance, means that most of the points are closer to the mean, and something with large variance or large standard deviation means that the average distance to the mean is large. All right. So that is average and that is a standard deviation, and those are two numbers that might be useful if we are talking about normal distributions. All right. Sometimes average can be deceiving. All right. It might be that two groups share averages, but one group has larger extremes values than others. That would be a difference in the standard deviation. So it has its limits as usefulness. All right. So now I was talking about data, right? In the example that I gave, I was talking about the scores on a test, right? And a score on a test, unless we have something very basic like letters A, B, C, D, usually are continuous, right? The scores. And in that sense, when the score is an observation, we call that observation a variable. And because it's continuous, i.e., there are no steps in between points, could be infinitely divisible. That's the idealized version. We call it continuous. And because it comes from a random distribution that we also ideally assign to a normal type of distribution, we call that a continuous random variable. Okay, so continuous random variables are probably the easier to understand. Height is a continuous random variable. It doesn't particularly follow a normal distribution, and it doesn't have to. Okay, but the weight of people is a continuous random distribution. The scores on the test, the speed of cars on the highway, those are continuous random variables. All right, they don't have to be normal or any particular distribution. They just have to be continuous, be random. This is come from a distribution that we don't know, and they are variable. So here is the idea that it's something that we can observe or measure. All right. So I'm sometimes mixing some ideas. We were talking about a variable. That the variable is sometimes the data that we're working with. So the data is a set of observations. All right. So in the case of the test, the observation was the score. All right. In the case of the score, that observation was a continuous random variable. Most data, also this applies to most variables, can be put into two groups. qualitative means that it can be indicated by a label. It means that it has probably it has a ranking, not necessarily. But if you think of the score that we said that it was a continuous variable, if we would like to make it qualitative, we would say, okay, people that have between 90% and 100% have an A. People that have between 80% and 90% have a B, and so on and so forth. We transformed that continuous set of data into a number of steps that we called qualitative. Okay. So that is one type of data, one type of variable. Another type of variable is quantitative. Okay. So this quantitative variable can be indicated as a number. All right. So the qualitative data might or not be indicated as a number, but the quantitative should. All right. And this is a similar idea, can be understood with discrete or continuous. Okay. So the qualitative data is always discrete. All right. The quantitative data might be continuous, meaning no steps in between. There's a bit of an art here because one can think of, for instance, time in years. All right. And sometimes your data only has years, like the first year, the second year, the third year, the fourth year. So you technically can divide that and have half a year, but there will be times in which it doesn't make sense to divide something that seems continuous. All right. So the continuity of the data can be a fuzzy idea, but in general, it will be obvious. Okay. Now, in that sense, these are not in any particular order, these items, but a discrete random variable is a random variable whose outcomes are counted. Okay, so meaning these would be items that we explicitly say out loud how many of those we have. So for instance, how many people are between 90% and 100%? That's a discrete variable because that's a number, that's a count. Okay, if we have counts, that variable is discrete. All right. Experimental unit. So here, everything is related. This is related to the idea of observable. Okay, the experimental unit is the thing that you can observe and measure, and in the case of the test, that's the score. Okay, the score is the thing that you observe, that you measure. Usually, it's the dependent variable. Okay, it's the thing that you cannot control. It's the thing that it's the outcome of the experiment. All right. And opposite to that, we have explanatory variable. Okay, this is the independent variable of the experiment that can be controlled. For instance, in a test, an explanatory variable could be hours of time, so a period of time in hours that students use to prepare the test. Okay, that would be an explanatory variable that you expect correlates with the experimental unit or observable variable that would be the results of this course. Okay. Now, numerical variables that take values that are indicated by numbers. Yep, that makes sense. Parameter, I think I already mentioned this idea. Now, parameter is a number that is used to represent a population characteristic. Okay, generally cannot be determined easily. Well, that depends. But when we started with average and standard deviation, I said the things that describe a particular set of data, that they describe it well. If it's a normal distribution, those are parameters. Okay, so the average and or mean and the standard deviations would be the two parameters that describe a normal distribution. But in general, parameters are just numbers that you can use to describe population characteristics, okay? And we will see today how those parameters can be used to quantify the strength of association between variables in an experiment, such as we're using the example of the scores in a test. Well, that score probably can be explained by the amount of time that the students used to prepare the test, and the strength of that relation can be quantified, and that will be assigned a parameter. Okay. Well, today won't be particularly relevant, but you should be aware of the concept of population. So those are all individuals and objects or measurements whose properties are being studied. Okay, but we can't access the population. Okay, so the population is not something that we can study. What we can study is a sample of the population, which I don't know if we will have that item here, but basically all of our research, all of our ideas, all of our models, or all of our inquiries will be related to samples of those populations. Okay, so those samples, hopefully representative of the population, are not the population, but should have the same properties. But because it's not the population, all of those things, properties, parameters, statistics that we will compute about the sample will have an associated error, okay? An associated uncertainty. If we had all the data, if we had the population, we wouldn't have an uncertainty in our discoveries. But because we rarely work with all the data, we always will have uncertainty with our measurements, with our predictions, with our anything. All right. Well, yes, here's sample, a subset of the population. So it here doesn't particularly describe that if this sample should be representative or not. But here we have the idea of sample bias, okay, where not all members of the population are equally likely to be selected. So let's say that we want to going back to the example of the test and the scores, let's say that we want to assign that the strength of the relation between time spent, time used studying and scoring the test, right? But let's say that we are doing this study across many universities in whichever country or in the world, and we can't access all those students to ask them how much time they use to prepare the test. So we go to just one university, and in the university we go just to the library, and in the library we find quote unquote random students to ask them how much time they used preparing the particular test. So we have various problems there. For one, we don't know if the particular university where we are asking these students for how much time they used is a representative university. But besides that, I guess the most glaring issue here is that we went to the library. So probably the students that go to the library, maybe they study more than the ones that they don't. So probably we will have a sample that is biased towards people that study more than expected, or than it's representative of the whole population. So when we sample our population, we need to be mindful of being as random as possible, so we don't have sample bias. All right. Now, so yeah, this concept sometimes is difficult to get, I believe. But so we are doing statistics, and in statistics there are things that are called statistics. Okay, so one statistic, singular, is a numerical characteristic of a sample. Okay, so if we are to guess the sample, or the mean of a sample, that mean would be a statistic. All right. If we do a test to assess if the means of two different samples are different between them, that mean difference would be assessed with a test that is called a T student. All right. And that T, that gives us an information of how different two means are between two samples, that T would be a statistic. Okay, so statistics is a numerical value that you quantify to estimate a population parameter. Okay. Okay, and finally, variable, anything of interest in a sample or population. Okay, but we already mentioned this a couple of times. Any questions about these items? No? All right. So let me share with you some data that I created, and let's see if I can share this file. David, any way in which I can share a file, not just my display?
Què vols dir, Jorge?
Si puc compartir un arxiu, un document de text.
Perquè se'l baixin o com?
Sí.
Al xat.
Al xat.
Sí.
El penjo directament al xat?
Sí.
Vale. All right. Nope. Ho intento arrastrar i tirar-lo al xat i no em deixa. Aquí ve que puc compartir un link. Si te l'envio a tu, David, per email, ràpid, el pots compartir?
Envia-me'l, intentaré i crearé un link, si de cas.
Vale. Perdoneu. Sorry, everyone. I'm just having difficulties with Teams at the moment that are unforeseen.
És que un Yamovi, un document de Yamovi o què és?
No, és arxiu de text. Bueno, potser el podria copiar i ja està. Bueno, sí. No te l'enviaré, el copiaré al chat. Més fàcil. A veure si em deixa copiar això, que és una mica llarg. Ups, massa llarg pel text. Em sentiu?
No el pots compartir com a l'altre document?
No, perquè és una que voldria que la gent obrís el Jamovi.
Ah.
Vale. Llavors, dona'm un segon. Sí. Mira. Vale. Ho he enviat al chat. Okay. So, all right, everyone. I'm sorry. This is probably not the most convenient way of sharing something, but I just sent a set of numbers through chat that I wish that you copy, and we're going to work with this in Jamovi for a sec. So everyone, I hope you have Jamovi installed, and you can copy this text, and I will show you how we can work with it in Jamovi for a second. All right. So if you have ever opened Jamovi until this point, this might be tiny for you. Let's see if I can make this larger. I'm not sure I can. Perquè, David, això es veu bastant petit, no? Imagino.
Sí, es veu molt petit.
Vale. Well, it's not particularly relevant that you can see exactly. You just should see that here there is a column with numbers. So everyone, I hope you can copy the text that I sent and paste it in the first column that you can see in Jamovi.
I'm sorry, I don't know if you have some problems with the data, because I tried to paste in Jamovi, but it just pasted in the first
file
square.
Row.
Yeah, in the first square.
Sí, dona un error, Jorge. No deixa.
No deixa? Ok. T'ho envio per email, David.
Envia'm fins i tot, si vols, al Jamovi directament. O sigui, ja, ho dic perquè si no estarà complicat.
Bueno, es que no està preparat el que vaig a fer ara en un arxiu de Jamovi.
No, aquest que tu tens.
Aquest que tinc jo, vale.
Aquest mateix.
Vale, doncs pegaré perquè també hi havia una altra columna per pegar, també la pegaré. Ok, dona un segon. All right. Give me a second. Save as. Okay, sent. Okay, for tomorrow I will have this solved, because you guys should experience the idea of at least pasting some data in Jamovi so you can work with it. All right.
I can fix it just pasting in Excel, and then I can copy and paste in Jamovi for everyone.
All right. Yes, that's probably because of the chat gets rid of the new line character and makes it all one line. So anyways, David maybe will share with you soon the Jamovi file so you can open it. ¿Ho tens, David?
Estic compartint.
Vale, perfecte. And please, everyone, feel free to ask questions. Otherwise, this will be very long and very dry for everyone if it's only me talking all the time. So I particularly devised this first session to be light on math, so we can ease our way into the topic. So I want this to be as easy to get into the topic as possible. So please feel free to ask at any point, interrupt me, because otherwise I don't know if the ideas are coming across well enough. All right.
Well, if you look at the chat, you have the file of Jamovi, so you can download it. It's WeTransfer.
Thank you. Does Universidad Autónoma have something like a virtual campus that we could use alternative to Teams? Just curious.
No, it's all Teams. We only have
Teams
for teaching.
All right.
For teaching, yes.
Okay.
Ja ho tenen, Jorge?
Sorry?
Ja tenen l'arxiu, ja pots començar.
Yeah.
Mira a veure si el pots ampliar perquè no es veu, jo almenys no el veig molt.
Vale. No, but the idea is that you just see the general thing that I'm going to do, but you should do it. So, but can you see that there is a column here, that is visible, or not? Yeah, because I'm not sure I can make this larger. I don't think that Jamovi has that feature. Oh, it does. All right. Okay, what about now? Hello? Can you guys hear me?
Yes, we can hear you.
All right.
Well.
So can you see my Jamovi well enough now?
Yes, we can.
Okay.
Yes.
Thank you for participating. I thought I was talking to the wall for a second. All right. So Jamovi has a very common setup that you can see that is very similar to Microsoft Office suite of apps. So here in the top of data is where you can work with exactly that data. Okay, so here in this first column is where I have pasted a set of data that I call watch time. Okay, that's the time in, you can say, hours that people may have seen your advert, right? Imagine that you are advertising something through YouTube ads, and every other, I don't know, week, hour, month, you collect how much people has watched your advert. Okay, and that will be your that will be one of the variables that you will consider. Okay, and so here we have this in column A. So if you double click on column A, double left click, Jamovi tells you, okay, that this variable is called A, but we can change this to watch time. We can say that this is hours. Okay, watch time hours. You can add a more descriptive set of information, but it won't show in the tab. Okay, now we have watch time hours. That's the variable. And B can be the number of clicks or the number of time that people access your website, if that is what you were advertising through YouTube ads, right? So this can be clicks. Okay, and so the idea is that this can be, for instance, your clicks per month. Okay, so this clicks per month should be, you can consider it either way, but clicks per month, it's probably makes sense for it to be the observable variable. Okay, the thing that you are interested about, the thing that you want to learn more about. So this would be your observable or dependent variable. Okay, and here Jamovi automatically assigns nominal, but we should probably give it a continuous label. Okay, now clicks per month, it's not technically continuous because you cannot have a click. This is what I meant with the fuzzy idea of continuity. But because you could have either number of clicks from 0 to infinity, it wouldn't make sense to have a ranking and to have like 1 click is totally different from 2 clicks and totally different from 3 clicks, and they are different levels. That doesn't make much sense. So here, this why we should say this is continuous. Okay. You could also assign this a set of levels if you decided this was ordinal, for instance. So you could say from 0 to 50, it's a little amount of clicks. From 50 to 100, it's a reasonable amount of clicks. From 100 to 200, that's a lot of clicks. That would be making this data set this variable not continuous, and we could do different things with it. But now we want to explore the idea of these two continuous variables and how they are related and what are their properties. Okay, so in the Word file that David shared with you, with the material that you could peruse, skim through before today, I'm going to the point that says descriptive statistics, key terms, chapter 2. Okay, so in chapter 2, we have a new set of ideas. Well, I won't share it with you because I'm sharing Jamovi already, but it's the file that starts with box plot and first quartile. I will share the link in chat. So now, for instance, here we see back again the idea of mean. Okay, so let's explore the mean of these two variables that we have here. So let's go to watch time in hours. Okay, so what we do is we were in the data tab. Okay, let's go to the analysis tab. So not data, analysis. And in analysis, we go to exploration. Okay, and in exploration, we go to descriptives. So this is a new window. And let's go with, okay, here we have C, which is that empty variable. We can delete that one if you want to. It doesn't make a difference. And in descriptives, we have an empty table because we didn't ask Jamovi to describe anything yet. All right. Now, let's say that we want to get the descriptive statistics from watch time. All right. So here we have the number of items in that set of data in that column, 976. We have missing values 0. It is very common that in real life data you will have missing values. Missing values correspond to people not answering that particular question in that particular questionnaire. All right, or missing value can be the answer was absolutely not appropriate to the question. So if you were expecting a word and you get a number, or vice versa, you can consider that a missing value. Okay, so that is part that is something that you should care about before you start working with data. So that's why you do the type of descriptive. This is to figure out if your data has the shape and behavior and the features that you expect of the things that you collected. So, okay, we have 0 missing items or 0 missing entries in this column, watch time in hours. Now, the mean of this data set is 2.04. That is the number of hours in average that your advert is seen in whatever period of time you collected this data. So if this is watch time in hours per month, the watch time of your advert per month in hours is 2.04, okay, in average. Now, we don't know if this number is representative or not of the sample because the mean, as I mentioned, is just a number that describes well normally distributed data, not necessarily describes well data that is not normally distributed, okay? If you remember, normal distribution is a distribution that has a bell shape, okay? So something that is less biased than the mean for describing data that is not normal, it's the median, okay? The median is a term that you will find in the link that I sent to you in this book, Introductory Statistics. And the median is a number that separates order data into halves, okay? Here, we don't necessarily have so this is a continuous data set, okay, of watch time, but you can imagine that there is a point that is exactly in the middle, okay? If people watch, so if the hours of watch time go from 0 to 100, there are a number of times that you observed 2 hours, a number of times that you observed 5 hours, and a number of times that you observed 7.5 hours, and a number of times that you observed 75. So you have many different observations, and you can have all those numbers in a row. And there is a number that it's in the middle, okay? And that number that it's in the middle, which is not the mean, it's called the median, okay? And the idea of the median is that it can be a better descriptor of your data, that number that it's in the middle of everything, because it's not as heavily swayed as the median towards extreme values, okay? So the mean can change a lot if you have unexpected amounts of extreme values, but the median won't, because the median is a number that it's in the middle, all right? You also have so this is the mean, the median, the standard deviation. The standard deviation is that number that tells us about the variance in the data, how far are in general the observations that we have from the mean that we compute, okay? And here we have minimum and maximum. So these are the minimum watch time and the maximum watch time that we have in this data, okay? So here we can give various, we can use any number of these options to have some more information, okay, about this data. For instance, here is why we have the mean, because we have mean selected, and why we have the median, okay? Here we can have also the variance, not particularly interesting if we already have the standard deviation, okay? We can have range, interquartile range, not particularly important for now, but what we should look into now, it's plots, okay? So this is the descriptive part of an analysis. Here is where you can get familiar with your data. So now we have some numbers about this data. We have the amount of items that we have in this list. We have the mean, the median, that they are very close together. And that is something that is a clue about what we are going to see now. Because what we can do with this data is draw a histogram, okay? So a histogram is, as you can read in the stats book that I shared, is a graphical representation in XY form of the distribution of the data, okay? So I've been talking about distributions a lot, and now this is the first time that we are going to have a view of what the distribution looks like in probably the best way of looking at a distribution, which is a histogram, all right? So this is the data that we have, all right? This is the density of that data, okay? So in between 0 and 1 hours, there is this amount of views, okay? So that is the density of the data plot in the y-axis. And in the x-axis, we have the watch time in hours, all right? So if you just have a little bit of imagination, you can sort of see the bell-shaped curve here, okay? I created this data myself. This is not real data. It's not ideal either because I added error to this data, so it would look more appropriate. But this is the sort of plot of histogram that you may see if your data is about normal, okay? We can do a test for normality, but maybe that is for another time. I will show you later what tests can be done for data. Okay, and looks can be deceiving. Data might seem normal and it won't be, and data might not seem normal and it will be. But in general, just with this descriptive, with this pictorial description of this data, we can have a sense that probably the mean is a good number to use to describe this data. Okay, and probably the median too. We can also see that it's a bit skewed, this data, so it's not as exactly symmetrical. But well, that's what you will find with real data sets. Okay, even though this is not real, this is just a simulation. We can do the same for the other data set. So we can swap. We can, instead of watch time, we see clicks per month. Okay, so clicks per month, definitely not normal. Okay, if you see this type of data, okay, which is not bell shape, all right, and this is something that you can look about it. Also, you can do box plots. Okay, so box plots is a similar idea to the histogram. Okay, but you should imagine that the box plot is like the histogram, but looked from the top. All right. This midpoint here, this line, is the median. Okay, so if we're looking at clicks per month, in between 100 and 200 is the number of clicks that's in the middle. Okay, inside the box, we have 50% of all the clicks. So per month, 75 of the observations that you do is that the clicks that you have are between 100 and 200. Okay, and these lines from 100 to 0 are 25% of the number of clicks that you observe. And here between 200 and 400, these are the amount of 25% of the clicks that you observe. Okay, so again, we have clicks per month. The clicks per month go from 0 to 400 and a bit more. The midpoint, the median, is between 100 and 200 in clicks per month. If we see the descriptive of clicks per month, we see that the median is 155. So we should expect this line to be around 155, which it is. All right. As I mentioned, the median divides the amount of observations. So 50% should be above the median and 50% should be below the median. All right. Then inside the box, there are 50% of observations, and outside, sorry, is that a question? The median is represented by the line. Am I not hearing something? If someone was asking.
No, son aclaracions que jo poso, no et preocupis.
Vale, okay.
Si venen per mi, don't worry.
Okay, so the median, yeah, exactly. The median is represented by this midline. It separates the data. Below it is 50% of the observations. Above it is 50% of the observations. And inside the box, we also have 50% of the observations. Okay. The remaining 25% are below the box, and the remaining 25% are above the box. And you might be curious about the points that are not inside the line. Okay, that might be outliers. Okay, so outlier is a term that we didn't see yet, but are points that are just are just described by a particular rule set. Okay, it has to do with the distance that those points have to the mean in terms of interquantile range, which is a difficult concept maybe now, but you should have the idea that those outliers are perhaps too far from the median. Okay, in a way that it's asymmetrical to the bottom part of the plot. So by definition, we say if the distance is this many times a term that is the interquantile range, we say, okay, perhaps those points are problematic. Okay, don't worry now about the interquantile range. Just consider the idea that we have a tool that with this box plot that can help us identify what points might be problematic in the sense that perhaps they don't particularly belong to our data set. But sometimes you just have outliers and you just have to deal with it. Okay, but if we had one point at 700, just the one, probably that was a mistake. Probably someone didn't collect that data properly. Probably maybe you had a problem in the software that was counting those clicks. You have to look more into that. So maybe the outliers are more like points of interest that might lead you to identify problems in your data set. But they are not necessarily bad points that you have to exclude. All right. So we explored here mean, median, outlier. So in the book says an observation that does not fit the rest of the data. Okay, there is a formula for it, but so you have actually outliers and extreme outliers. But not particularly important now. So when I was saying the first 25%, this second 25%, and the third 25%, and the fourth 25%, okay, those are quartiles, okay? Those divide all right. So those quartiles, they are called like that because divide the data set in 4 parts. Okay. So each one of these lines, or basically in the box plot, describe the quartiles. And well, we already talked about the standard deviation and variance. Okay, so here in the book is described interquantile range. Is the range of the middle 50% of the data values. Okay, so the interquantile range is the range between the first 25% and the 75%, and you just use a formula to yeah, that's a good picture. You just use a formula that is there. So very good. So if the point is farther away from the third quartile more than a number of times the interquartile range is an outlier. And then, but this is a bit sui generis. So that 1.5 made up. Okay, that 1.5 doesn't follow any reason other than people decided that more than 1.5 it's an outlier, and I don't remember now exactly, but I believe it's 2 or maybe another number made up that describes an extreme outlier. Okay, so just consider the fact that outliers are points that you should look into, not necessarily bad information. Okay, so let's move on to the next set of key terms. Well, perhaps we shouldn't, and we should stay here for a second. So let's look at this data again. So here we have watch time in hours, clicks per month, and I imagine you guys have an idea of what is going to happen if we try to investigate how are these data related. All right. So a reasonable working hypothesis is that the larger the watch time, the larger the amount of clicks that I will have on my website per month. Right. That is a reasonable working hypothesis. All right. Now, how do we test this hypothesis? So the first thing that you should do, besides this descriptive exploratory step to see how your data behaves, if you have any missing values or outliers, is doing an analysis of correlation of this data. Okay, so if we go to analysis in Jamovi, you will see that in the regression toolset, there is the correlation matrix. Okay. So when every time that you open a new tool in Jamovi, it will create this empty table that you can fill with your data or the analysis particular to your data. So in this case, we only have 2 variables, so that makes it easy. And we just select both of them. And immediately we have this matrix created here. So this matrix, it's kind of pointless in this situation. We just only need these 2 values because we only have 2 variables. Okay. And we have here 2 numbers. The output of this most basic correlation analysis is 2 numbers. One is the Pearson's R, or correlation coefficient, and the other one is the p-value. Okay, so the p-value, I'm going to describe it to you because it's very important to understand what it means, because everyone, well, at least in my field, in either in biology or psychology or biostatistics, people are kind of obsessed with p-values. I'm not sure in your field what is the situation, but p-values is something that people obsess about. So the idea here is that there is an hypothesis. Okay, the hypothesis. Before we did this analysis, I mentioned something called the working hypothesis, right? So the working hypothesis is that these 2 variables are correlated. Okay, you shouldn't confuse your working hypothesis with something called the null hypothesis, right? So the null hypothesis, oftenly symbolized as H sub 0, is the hypothesis of nothing is happening. There is no relation here, nothing relevant about these 2 variables. Okay, so there is the null hypothesis is there is nothing to see. Okay, and the p-value is the probability of that being true given the observations that you have seen. Okay, so our observations are watch time and clicks. Okay, we have a Pearson's R, that is our observation. This number could has a distribution, and that could be an extreme value or not. But the essence of the p-value, if not perfectly defined with these words, is the probability of observing that result and your null hypothesis being true. So if your null hypothesis is there is no relation here between these two variables, well, that is very unlikely. Okay. So that gives strength to your working hypothesis. Your working hypothesis being there is a relation between these two variables. This working hypothesis is often called alternative hypothesis, so alternative to the null, and it's often symbolized with H sub A, okay, subscript A. So now, because I really want you to do this, if you didn't open the file, please open it. Have these two columns open. Then go to analysis, regression, correlation matrix. Okay, and I really want you to select these two variables, and hopefully you can have this table so we can see a bit more about it. So I give you a couple of minutes for that, so you guys can follow with the software too. And I know it's difficult, particularly if you have just the one screen. It's difficult to see what I'm doing and also do it yourselves. So I give you some time for you to do that. And please ask any question if you want to. Okay, now that I have introduced the idea of p-value, I want to go back to an idea that we mentioned before. Okay, so if we go to the data to watch time, and if we want to do descriptive analysis of it as we did before, and we want to plot that histogram, there is a normality test. All right. So although I created this data to be normal, that was my intention, because I added some error and because I modified part of it so the watch time wouldn't be negative, accidentally I made this data not normal. Okay, so the way of assessing if a data set is normal or not is the normality test. It's called Shapiro-Wilcoxon test. And well, here is the result of the Shapiro-Wilk. And the result, technically the result of the test is this W, 0.99. Okay, that's not very useful to you. The most important thing is this p-value. Okay, so the p-values are these probabilities associated to the observations of the statistics that you get from a test. In this case is the W of the Shapiro-Wilk test. Now, for this test, the null hypothesis is that this data is normal, okay? And if that is true, the probability of observing this W is lower than 0.001, okay? So unlikely, okay? So it is unlikely that this data, if it came from a real population, it would be normal, okay? So well, it's not very relevant to what we're going to do next, but I meant for this data to be normal, but when I added the error and removed values below 0, I made it not normal, and this is the result that we observe, okay? So again, the p-values are difficult concept, are a probability of observing, technically, are a probability of observing a result at least as extreme as the one that we are observing. That is a proper definition. The result that we are observing for this normality test is the W 0.99. Associated to this particular data set, if the null hypothesis of normality was true, the probability of observing this is very low. Therefore, we reject that idea and we say that this data is not normal. Okay. Now, I hope you had time to have your 2 columns. Now we're going to go to analysis, regression, and we are going to draw a plot that I believe that David already shared in chat, which is in exploration scatter plot. Okay, so we here technically is irrelevant which you choose as y-axis and x-axis, because the thing that we want to explore now is what is the type of relation between these 2 variables. But we can do it well from the beginning and decide that clicks is the thing that we care about, is the dependent variable, the thing that depends on watch time of the advert, okay? So we're going to put this on the y-axis as response, but not relevant in this step, and in the x-axis, the watch time, okay? So, as I mentioned, I made this data up. This is why it looks so nice. All right. So before ever starting a linear regression analysis, which is what we want to try to learn today, what we need to learn, okay, what we need to find out is if it's really reasonable to say, to explore the linearity of the relation, of the strength of the relation between 2 variables. All right. If this had a totally different shape, okay, let's say that this had an S shape, or let's say that this has a plateau. Oh, so it starts linear, but then it fades away. Or you can imagine any shape that it's not like this, that it doesn't look like it hovers above a straight line. Any other shape perhaps would be indicative that a linear regression model is not the best choice. All right. So before going ahead with that, we try to assess if we have a legitimate reason to using a straight line to model this the relationship between these 2 data. Okay. So without going into the numbers, in this plot, you can use the option linear to draw that line. Okay, so we are not into the linear regression part yet, but this line is the line that best fits this data, which is somewhat of a maybe difficult concept, but the idea is that there is a line, okay? There is a line that we can draw on top of this cloud of points that minimizes the overall distance from the points to the line, okay? If we draw from this black line another set of lines to each one of the points, okay? So if we draw from the black line perpendicular lines to every point in this chart, and if we measured that distance global from the line to all the points, the line that best fits this set of points is the one that minimizes the overall distance, okay? That is the sum of least squares. That is the concept. I don't want to overwhelm you with the math yet. That's probably for tomorrow. But today I want just for you to have the idea that there is an overall distance from the points to the line. This distance can be great if we drew the line anywhere, okay? And this distance can be made smaller and smaller. The best we draw this line, and the best option of all is the one that minimizes that distance, okay? The line that minimizes the overall distance to the points is the one that it's the result of the linear regression analysis, which can be seen as a linear optimization, okay? Because the thing that you are optimizing is the distance from the points to the line, okay? So we can see that in regression. So if we go back to linear regression, which if we go for the first time to the linear regression option in the regression tools, we can assign what we think is a dependent variable and what we think is what we think is the dependent variable and what we think are the independent variables here in covariates. And today we are not going to go into factors, okay? Just two variables that are both continuous and just the two, okay? So we decided that the thing that we observe is the clicks per month. That's what we're going to call the dependent variable. And we decided that the thing that we think is the independent variable that determines how many clicks should we get to our website is the watch time in hours in our advert. And this is the result that we get with the basic output of linear regression. First is the R. This R is the Pearson's R, okay? So if we go back, you see that our 0.82 in the R of the linear regression is the 0.82 from Pearson's R. And we get another thing, which is the R squared, okay? Which is 0.67. So this R squared goes from 0 to 1, okay? Unlike the Pearson's R, which goes to -1 to 1. So in this case, because the correlation is positive, meaning that when the variable in the y-axis grows, the value in the x-axis grows, or vice versa, we say that the relation is positive, okay? That's also why the slope, i.e. the angle of this line is what it is, okay, +2. Meaning that the correlation coefficient could be 1 if this set of points was in a straight line and the relation and the correlation was positive and absolutely ideal, so 1, but it could be also -1. Okay, it could be -1 is if when watch time increases, clicks decrease. Okay, but the R squared, it's different. It can only go from 0 to 1. Okay, and the R squared, it's not the strength of the relation between the two variables. It doesn't give us a direction. It doesn't say if they are positively correlated or negatively correlated, unlike the Pearson's R. But what it tells us is the percentage of the variance in the observable variable that our predictor variable correctly predicts inside the model. Okay, correctly explains inside the model. So basically, the clicks per month have a variance. Okay, so they have a spread. Okay, we saw the histogram of the clicks per month. They are not just in one point. And the watch time hours also vary. Our idea is to explain how much these clicks change per month, given the watch time in hours in that month, and the amount of that variance that we can explain just with the watch hours is the R squared. Okay? Any questions until this point? I'm sure there must be at least one question.
I'm sorry. Could you just please explain the R square again? I kind of got a little bit lost in that. Thank you.
No problem. So the R squared, it's the square of this R. That doesn't give you anything. But the meaning of this R squared is how much can you explain your clicks per month given your watch time in hours. Okay, so listen, this month I had these many hours of watch time of my advert. Okay, this many hours, I know, 3. And okay, that gives me that if you draw a perpendicular line from the 3 to the regression line, it puts you around 200 or more clicks per month. That's the thing that you expect after this simple linear regression model, right? If this is the line that best fits your data, with 3 hours of watch time, you expect this number of clicks per month. Yeah, but you observe not only 200 and something clicks per month. For 3 hours, there are very many observations that are not 200 clicks per month or a bit more. So if the data that you observed was exactly or above that regression line, you will be explaining every observation that you have with your regression line. But because you have a cloud of points, you don't have a straight line of points, you are not explaining everything. There is something that it's missing. There is something that we will call random that you don't understand yet. And it's not explained by the watch time. And that thing that you don't know makes the clicks change. So not only watch time is relevant for the amount of clicks that you get. Okay, so there might be other relevant variables that you are not considering, or there must be just some randomness that you cannot explain. But the thing is, if to the question of how much of your clicks per month can you explain with your watch time, 67%. That's the R squared. Okay, it gives you the percentage of the variance of your observable variable that can be explained with your independent variables. In this case, just the one, watch time. Okay.
Thank you. Thank you.
You're welcome. Now, so here, so there is, I'm not going to go into a formula yet, but let's go to, not model builder. Okay. Now, this seems rather obvious that this works, okay? Seems rather obvious that a line is a good description of the relationship between these two variables, okay? But we may want to be sure, so we can do an overall model test. So we can test how reasonable is our assertion, okay? And when you do the F test, you get the F statistic. Don't worry about it. The important thing is that F statistic has a probability associated to it. Okay, so the null hypothesis being these two variables are not related at all. Okay, that being the null hypothesis. This is the observation that you make, the F statistic. Yeah. What is the probability of observing something like this or more extreme and my variables not being related at all? Well, smaller than 0.01. Okay, so this is the idea of the p-value that is associated to a statistic when you do a test, an hypothesis test. All right, so here the null hypothesis is my variables are not correlated. This is the observation, an F of 1900. And the probability of observing that or a more extreme value and your variables not being correlated is very, very low. Okay. Now, how much is very, very low? Up to you. It depends on the field. Okay. So in biology, they usually in psychology, they usually use a cutoff of 5%, okay, or 0.05. If your p-value is 0.05, which is 5% or 1 in 20, if it's smaller than that, your observation has a statistical significance because someone decided that that is the point, okay? But in physics, it's different. In physics, you need smaller values of p-value to decide that some relation is significant, okay? So that depends on your field to decide if an observation has is significant or not, depending on the p-value. But it's probably safe to say that it's 5% or 0.05. So if the p-value is lower than 0.05 for a particular test, in this case, this F statistic to assess the reasonableness of our assertion that these two variables are correlated, well, it's so low that is likely that our variables are indeed linearly correlated. Okay. Now, there are other parameters that we can get with this analysis. The other one is the adjusted R-squared. So the adjusted R-squared is not relevant if we are not comparing models of different amount of parameters. But basically, if you say, I don't only have watch time, I also have the age. Sorry, I not only have watch time, I also have the timestamp on when my advert was seen. So perhaps you think that your advert is more enticing to people that see it after dinner, or perhaps you think that your advert is more enticing to people that see it before breakfast. So you can have other variables that may try to predict how people would click in your website. And if you have many of those, you may want to use this adjusted R-squared that assesses the goodness of the fit. So how good is your model, and weights how many variables are you using to explain your dependent variable, okay? Because every time that you add complexity to a model, the fit will improve, okay? But not necessarily not necessarily enough to justify adding the variable, okay? That goes to the idea of Occam's razor, okay? It's that the best explanation is usually the simplest explanation, okay? It doesn't mean that always just one variable works. It means that you have to justify with an enough better fit the fact of adding variables, okay? And we are going to see this at the end of the class with a real data set, and you will be able to decide if adding a set of a variable works or is justified with your data, okay? So one thing that you can get, so well, the thing that we get here is a model, okay? When we do linear regression, the real output, besides the R-squared, which is relevant, besides the F statistic for the overall model test to see if the linear regression is appropriate, what we get is a model, okay? So let me share with you a couple of slides. Or perhaps I should go into presentation mode. But I'm sharing them. All right, let's see. Give me a second here. All right, so now we start into the idea of having a model, okay? So a model is an approximated representation of reality, okay? In that case, even if it was fake data, let's imagine that it's real. And we decide that we want to investigate how well we can predict our clicks per month based on watch time of our advert, all right? And well, that's probably not the only thing that makes your clicks per month change, definitely. So you just do your best guess, all right? And decide, okay, this is the only variable that I'm going to explore. Perhaps you should explore more. At any rate, whatever thing you do is going to be an approximation of reality. Always there's going to be an error, okay? Because not to have an error, you need a model as complex as the universe, okay? So obviously, you cannot go that complex. So with the level of simplicity that you may use or the level of complexity that you consider relevant, you do a simplified, idealized approximation of reality. All right. We use data to create the model. In this case, to fit a line to it, that thing that we call the regression line that we obtain by minimizing the distance to the cloud of points to the line, which is a linear optimization problem or least squares problem. And that model, then we can use it to make, hopefully, valid predictions, okay? So there is a famous quote by a statistician, George E.P. Box, that all models are wrong, but some are useful, okay? So never a model will be a perfect representation of reality, because the true representation of reality, it is reality, okay? There is no alternative to that. So your model will always have error. The thing is that sometimes that will be enough, right? So the models that we are going to use in these sessions all have the same shape. All are first to the left of an equal. We have the effect or variable that we want to predict that we call dependent. And to the right of the equal, we have a function, which now is going to be a linear function, okay? Because we are doing linear regression, that is going to have as arguments, so the things that are going to modify the function are going to be predictor variables. In the case of the predictor variables for the one case that we are doing now, the prediction of the clicks in function of hours of watch time, the independent variable is hours of watch time, and a set of parameters, okay? So the parameters in the linear model that we are considering now with Jamovi, there are only two, because that's enough to draw a straight line with only one variable, okay? So the two values that we need are called the slope and the intercept, okay? So I already mentioned the slope. The slope is how slanted is your line, and the intercept is where that line cuts the y-axis. But I'm going to explain that further in a second. And the other thing that we are missing is the error, okay? I mentioned all statistical models have error. You cannot get out of that. And that is the thing that you want to minimize, okay? But you will never get rid of it. So here, for our linear model, we have the continuous random variable, which is clicks clicks in your website. The explanatory variable, which is the watch time, and the parameters, which are mentioned, I already mentioned, the slope and the intercept, okay? So we already did this. This is the scatter plot. This is the thing that we need to do before looking ahead to trying to predict values of y by using values of x. So before trying to predict clicks per month, we want to establish that there is a linear relationship between watch time and clicks, which we did. And that is what we do with the correlation. And the step that we are at now, the state that we are at now is the regression model. And for the regression model, we have a set of assumptions that we didn't check yet, but we are going to do now, okay? There are relevant for at this point are the autocorrelation test and normality test, and not now collinearity, because we only have one explanatory variable. But I'm going to show you now what I'm talking about. So if we go back to Jamovi, here we have the assumption checks. Okay, so now the ones that we are going to do is the autocorrelation test. Okay, so here we basically want to assess that observations in clicks per month are not autocorrelated, meaning that an observation doesn't give you information about the next observation. Okay, so give me just 1 second because I want to confirm one thing. And you're welcome to ask any questions. No questions? Okay, so remember that I said that when we do any types of these tests, we have an statistic and a null hypothesis and a p-value associated to that statistic. Okay, so the null hypothesis here, usually the null hypothesis is there is no correlation, or there is no relation, or these things are independent, or so there is nothing to see here. That is a null hypothesis in general. Okay, so when we do the autocorrelation test, what we observe is that the p-value is high for this particular statistic from the Durbin-Watson test. Okay, so if the null hypothesis is there is no autocorrelation and the result of the test is 2.06, the probability of the null hypothesis being true and observing this is 42%. Okay, so it's very high. Therefore, we can't reject it. Okay, we can't. So this sentence is going to be complicated, I believe. We can't reject the idea that this variable clicks per minute is not autocorrelated. Okay, so we can't reject the idea that there is no autocorrelation. Okay, therefore we are good, because if we had autocorrelation, we would have a problem. Now there is a normality test. Okay, and the normality test, the null hypothesis is that the test is, sorry, this is a test for the, or I should explain residuals first, sorry. So we mentioned that we wanted to obtain a line that minimizes the distance from it to all of the points, okay? A distance that is computed with a perpendicular line. When we do that, those distances are basically explained, are represented with something that we call residuals, okay? So these are the these are the residuals. So these are the distances. I'm not sure if this is easy to see, but these are the distances from the points to the line, okay? It's a weird concept. So on one plot, we have the line over the observations, and here we have plotted the distances to the line that we created, okay? The thing is, if our data can be well approximated with a linear regression, we shouldn't see any tendencies here. So tendencies is anything that is not just a cloud. So anything that is not just a cloud of points has some sort of tendency, and that is not good for residuals if you are using a linear regression model. Okay. Not only that, not only there should be no tendency, these residuals should be normally distributed. Okay. And this is what we have with the normality test. Okay. Here, the normality test, the null hypothesis is our residuals are normally distributed, and the probability of that being true is unobserving the statistic that we observe, which is 1, is 0.14. Hence, we can't reject the idea. Therefore, we're fine because we want the residuals to be normal. Otherwise, the linear regression, it's not a good tool to approximate this data. Okay. Another thing that we have here is Cook distance. So here, this data is so ideal that we don't see anything here. But Cook distance is a measure of it's another measure of those outliers that we were talking about before. So probably when we start working with real data, we are going to see more into Cook's distance. But yeah, Cook's distance is a measure of the leverage that points have on your drawn line. Okay, you can imagine that if we had an absolute outlier in a month that the watch time was 3, but the clicks were 1,000, and we had a point over here at the top of the chart, that would be definitely something to look into, probably something to get rid of, and something that would have a huge leverage on our straight line, because what we want to do is minimizing distances from the line to the points. So if we have a point that it's so far away that to minimize the distance, we are skewing the whole regression, that point has a lot of leverage. That point has a high Cook distance, and that's probably a point we have to deal with. All right. So I will say that if you have questions, you should ask. And I will give you maybe 5 minutes of intermission here, so you can think about everything I've said. Maybe you can fix a bit your notes. Yeah, and please consider asking questions. All right. And if that's okay with you, David, I will continue in 5 minutes.
Ok, fem una pausa llavors.
Good.